Welcome again to the class. We have been discussing the deflection of the beams, and in the previous class, we started with the deflection of statically indeterminate beams. Let's solve a few more problems to understand how we find the deflection of statically indeterminate beams, and we'll be taking problem 12.17. As far as problem 12.17 is concerned, problem 12.17 is a cantilever beam having roller support at its pre-end A. Therefore, as we have already discussed in the previous class, that this type of a beam, cantilever beam having roller or pin support at one of its end, that's at its free end, is a statically indeterminate beam. This is a statically indeterminate beam. Now this statically indeterminate beam is being subjected to a triangularly distributed load, and we have been asked to find, we have to find the reactions at the ends. We have to find what is the reaction at end A, what is the reaction at end B, and we have also to calculate, okay, we have to calculate Ra, we have to calculate Rb. Apart from Ra and Rb calculation, we also have to find its deflection curve. In order to solve this question, what we will do, let's first of all try to understand the type of loading on the beam. As far as the load on the beam is concerned, the load on the beam is a concentrated load. Therefore, the load on the beam is a triangularly distributed load. We know a distributed load can be replaced by a single load whose resultant, whose magnitude is equal to the area under the load diagram, and it acts at a point called the centroid. As far as the magnitude of this load is concerned, the magnitude of this load will be the area under this triangle, that is half of base into perpendicular. Its perpendicular is W naught, half of base into perpendicular, and its perpendicular is L. This is the magnitude of the load, okay? This is the magnitude of the load that is acting on this beam. That is, this triangularly distributed load can be replaced by a single load having magnitude equal half of W naught into L. And this load will be acting at its centroid. And we know, as far as the centroid of a right angle triangle is concerned, the centroid of a right angle triangle acts from the 90-degree end. It acts at a point whose distance is L by 3. That is, this distance is equal to L by 3. Okay. Therefore, this entire load can be replaced by a single load, as is given here. Its magnitude is 1/2 of W naught into L, and it acts at a distance L by 3 from the 90-degree end, because we know centroid of a right angle triangle is at a distance L by 3 from the 90-degree angle. Therefore, this distance will be 2/3 of the L. Now, the reaction that will be offered will be having reaction at this end. Since this reaction is along y-axis, it's AY. You can also call this as RA, no problem. And at the fixed end, we will be having reaction at fixed end. That's what we will be calling as RB, or what has been written here as BY. It's your choice. You can write this as RB or BY. And apart from these two reactions, there will be one more reaction. That's what you call as the moment, because at the fixed end, we also have the moment, and the moment will be, and as far as the moment is concerned, at the fixed end, the moment is MB. Okay, because we know at the fixed end of the cantilever beam, we have the moment, that is MB. We are not concerned about this BX too much, because the beam, as far as the roller support is concerned, the roller support tends to roll along x-axis. At this end, there will be the reaction. Okay, the reaction will tend to stop it. Okay, let's discuss this BX later on. So as far as now the overall concept is concerned, we'll be writing the equations of equilibrium. That is, we will write RA or AY. Since this has given as AY, we'll also write AY is to be found. AY, BY, and BMB. They are the reactions whose magnitude we have to find. Okay. So what we'll be doing is, let's do the analysis as we have been doing previously. That is, let's cut a section in the beam. We neither know AY, we neither know BY, nor we know this MB. So what we will do, we'll take a section of the beam. As we take a section out here, this section we are taking at a distance X. Okay, from this end we are going to a distance X. Okay, we are taking a section out here. The section has been taken out here. Okay, the section is here. Now at this section, let the shear force be V. Let's suppose the shear force is V, And let's suppose at this end the bending moment is m. Okay, we have shear force V and we have bending moment m. Okay, so at this end we have shear force V and we have bending moment m, the way we have been doing. Now since we have a triangularly distributed load here, okay, we have to find out how much is the intensity of the load acting in this region whose length is equal to x. Okay, we can easily find it when the total length is L. Okay, at a length of L, the load magnitude is W naught. When length will be 1 unit, the intensity of the load will be W naught by L. When the length is X, it will be W naught by L into X. So it means at this very end, okay, at a distance X from end A, the intensity of the load will be W naught X by L. Okay, so this is a triangularly distributed load. Here the magnitude will be W naught X by L. Therefore, this triangularly distributed load can itself be replaced by a single load whose magnitude will be the area under the triangle, that is half of base, that is X, into perpendicular, that is W naught X by L, that is W naught X square by 2L, that is W naught X square by 2L. And this will be acting again at the centroid. Okay, centroid from the 90-degree angle is at a distance 1/3 of the base, that is X by 3. So this is how the analysis has been performed. So it means as far as this concentrated load is concerned, the section we had taken here at a distance X, okay, at this section we have said the shear forces, that the shear force is V, bending moment is M. So now we can write this bending moment as taking moments about an axis passing through point A. We can write the moment is M. This is anti-clockwise. We'll take this as positive. The moment because of this V, okay, or before we write this equation, we can also write the equation of equilibrium for forces as this V is acting downwards. Therefore, this will be minus V. And this 1 by 2 W naught X square by L is also acting downwards. This will also be taken as negative. W naught X square by L is also negative. This is equal to 0. So as far as V is equal, V is equal 1/2 of, but minus 1/2 of W naught X square by L. This is the value of V. Now taking moments about an axis passing through point O, we have moment because of moment M. Moment because of this V, this will be this V is trying to rotate it clockwise. Therefore, we'll write this as minus V into X. Okay, and the moment because of this 1/2, it will be 1 by 2 W naught X square by L, 1/2 W naught X square by L, and it acts at a distance from here to here. The distance is 2 by 3rd. Okay, this is 2/3 of X. So this is the moments. The summation of all these moments has to be equal to 0. Therefore, we'll write M becomes equal to V into X. Okay, so that's equal V into X, V into X, V into X. This is plus 2 and 2 will cancel. This is 3 to the 6. That is 1 by 6 W naught X cube into X will become X cube. 1 by 6 W naught X cube by L. Okay. This is, now we have to be very careful about the units. As far as V is concerned, this M is anti-clockwise. We have taken it positive. The moment because of this V will be V into X. This is clockwise. Okay, this is V into X is clockwise. That's why this has been taken as negative. And the moment because of this what we call as there is V into X. Okay, that's fine. V into X into this. As far as this V is concerned, this equation is fine with us. Now we have to be careful about this M, this V. Look here, we have to make a little change here in the V that we have found. We have not taken this AY into consideration. This, once we are writing the equations of equilibrium, we will write AY is upwards. This is AY. We have to take AY also into consideration. This V is downwards. This is minus V. And we have 1/2 of minus 1 by 2 W naught, 1/2 of W naught X square by L, okay, is equal to 0 when we write the equation of equilibrium. Therefore, V will become equal to ay minus w naught x square by w naught x square by 12. Okay, this is the value of our v. We'll substitute this value of v here in this equation to get the value of m. So we'll get m is equal to v, that is ay minus w naught x square by 12. This is v into x, this multiplied by x, this multiplied by x, plus 1 by 6 of w naught x square, 1 by 6 of w naught x cube, w naught x cube by L. Okay, so once you do the simplification, you will get m is equal ay into x, that is here ay into x, that is then w naught x cube by L minus 1 by 6 w naught x cube by L. Okay, that will be minus 1 by 6 w naught x cube by L. Okay, this will be our equation of the our equation of the bending moment. Okay, so this is our equation of bending moment. So this equation of bending moment we have to obtain. First we draw this section. Okay, once we are obtaining this equation, then the process will be same. We know the equation of the elastic curve is ei d2 nu by dx2 is equal to m. M is there. Okay, perform the integration once. Ay integration of x will be x square by 2, and the integration of this will be 1 by 24 w naught x raised power 4 by L plus constant of integration c1. Perform integration again. Perform the integration again. As we perform the integration again, we'll get ei nu, that this is the equation of the deflection curve, c1x plus c2. Okay, now in order to find the values of c1 and c2, we should know the boundary conditions. The boundary conditions that we have in this case are: at this end a, at x is equal to 0, at this end a, at x is equal to 0, the value of our deflection is 0. Okay, and at x is equal to L, again the value of the deflection is 0. The beam does not deflect at the supports. Okay, so we'll apply these equations here as is given here. As we apply the equations in this case here, the first equation will be: at x is equal to 0, at x is equal to 0, the value of our deflection is 0. The value of deflection is equal to 0. Once we apply this equation, what we will obtain: at x is equal to 0, the value of deflection is equal to 0. So we are here at put the value of x is equal to 0. This term will become 0. This term will become 0. This term will become 0 for x is equal to 0. And for this value, the value of our deflection is also equal to 0. Therefore, we can directly get the value of C2 becomes equal to 0 from this, as is given here. Okay. So our first constant, that is this constant, is equal to 0. Now again, go to x is equal to L. And we know, apply the second boundary condition. At x is equal to L, the value of our deflection is equal to 0. So in this equation, what we'll be doing, in this equation, substitute the value of x is equal to L. So x is equal to L, substitute here. So substitute x is equal to L, substitute x is equal to L, C2 is already equal to 0. And at x is equal to L, the value of our deflection is equal to 0. Okay. So from this equation, since our C2 is already equal to 0, so from this equation, we can get the value of C1. And the value of C1 will be this. Okay. This is the value for C1. Substitute the value of C1. Substitute the value of C2 is 0. We need not to write now C2. Substitute the value of C1. Substitute the value of C1 back in this equation. Okay. Substitute the value of C1. We will get deflection nu is equal to 1 by EI, and the expression. Okay. And the expression, that is this expression will obtain here. So this is the deflection curve. Okay. So this is how we have obtained the deflection curve. Apart from this, by the way, once we are, very important thing is that we have to clear here. That is, when you are writing that x is equal to L, nu equal to 0. When you write this, x is equal to L, nu equal to 0, and you are substituting the value of x is equal to L in this equation, and your left hand side is equal to 0 because at x is equal to deflection is 0. Now you have two redundants here. You have to find the value of C1 as well as AY. Okay, AY is the reaction. So what we will be doing, we have now, actually we have in these two equations, we have C1 is one C1 is one constant we have to find. We have to find the value of C2. Okay, this is 2, and we have to find this AY because this AY is also coming in our equation. So we need 3 equations. That's okay. We need not to worry about this equation because the boundary conditions that we have are x is equal to 0. At x is equal to 0, the value of our deflection is equal to 0. At x is equal to L, again the value of our deflection is equal to 0. Okay, and if you look at x is equal to 0, if you return back to the deflection curve, or x is equal to L, that's very important. If you return back to x is equal to L, we will say at this point, x is equal at the fixed end. Okay, the deflection curve at the fixed end, curve deflects like this. Okay, the points which are very close to this fixed end do not deflect at all. Okay, that is initially the point B. Before the application of load, point B was here. After the application of the load, the point B is still here. Okay, so it means if we draw the tangent, initially before the application of the load, the tangent was in this direction, and after the application of the load, the tangent maintains its direction. Okay, so it means at x is equal to L, we don't have an angle. There is no angle between the two tangents before and after the application of load. Therefore, the slope d nu by dx, the slope is equal to 0, which is not the case at point A. At point A, before the application of the load, the tangent was in this direction. As we apply the load, the tangent becomes in this direction. So at end A, the slope d nu by dx has some value. It is not equal to 0, but at end B, d nu by dx is equal to 0. This is one more boundary condition for us. So this is what is given here. So the boundary conditions that we are applying are like, we have the boundary condition x is equal to 0, the value of the deflection is equal to 0. Okay, at x is equal to 0, nu equal to 0, we are applying here. At x is equal to L, the value of the deflection is again equal to 0, we are applying this here. And in this equation, d nu by dx is equal to 0. d nu by dx is equal to 0 at x is equal to L. So substitute the value of x is equal to L, substitute the value of x is equal to L in this equation. You will get the relationship between AY and C1. In this equation, substitute the value of x is equal to L, so x is equal to L, x is equal to L, your value of deflection is 0. From this equation, you will get the relationship between AY and C1. Now we have two equations having two unknowns, AY and C1. Therefore, from solving these two equations, you will get the value of AY and C1. A1, AY will come out 110 W0 L, and C1 is this much. So solving this question, you have obtained the equation of the deflection curve. You have obtained the value of AY or RA. So what is this AY or RA? AY or RA is the reaction at end A. This is what you have to do. So for this type of beam, what has been done? For this type of beam, we have found the reaction at end A. Okay. We have also found the equation of the deflection curve while the beam was statically indeterminate. Okay. In the same way, the next unsolved solved problem is out there. I request my students to please solve this problem yourself. The boundary conditions, you have to do the same way, the procedure, you have to write the equations of equilibrium, but the boundary conditions you will be having, deflection will be 0 at x is equal to 0. Okay. Deflection will be 0 at x is equal to L. This is two second boundary conditions. Slope of the d nu by dx will be equal to 0. d nu by dx will be equal to 0, both at x is equal to 0 and x is equal to L. Okay, so you have 4 boundary conditions for this type of a beam. I request my students to solve this question themselves, and if they have any problem, they can return back to me. That's all for today. Thank you very much.